Thanks for being with us here today. Could you start off by just telling us a bit about your work?
So I'm a cosmologist, which means I study the universe as a whole. I try and understand the laws of physics from observing the cool experiments that are going on up in space. Because space does all sorts of experiments for us on time scales and energy scales and length scales that we just can't possibly hope to achieve here on Earth, and frankly don't want to. We don't want to explode stars here, we don't want to merge black holes here, but we go up, if you look up in space, all of those things are happening naturally, and we get the privilege of watching them and learning more about fundamental physics by looking up. So that's the reason that I get excited about astrophysics and cosmology, is all of the cool stuff we can learn about how physics works down here on Earth. The things that I study specifically, I'm really interested in trying to understand dark energy and dark matter. So these are dark aspects of the universe. There's a whole bunch of stuff out there that we can see, but there's much, much more that we can't. For some reason, there's stuff out there that doesn't emit light, so we study it by the fact that it has a gravitational effect on the stuff that we can see. But yeah, it's a mystery as to what it actually is.
So could you tell us a bit more about dark matter and dark energy?
Yeah, so there's two things that we call dark, and they're quite different. Firstly, dark matter was basically, as soon as we knew galaxies were galaxies, like as soon as we knew these like spiral nebulae that were up in the sky, were whole stellar systems really, really far away from us, people observed that they were moving in a weird way. They were moving far too fast to be held together. So Fritz Zwicky in the 1930s was the first to notice that galaxies orbiting each other in big clusters of galaxies were moving faster than could be explained by the amount of gravity that you would expect from the galaxies themselves. Later on, Vera Rubin in the 60s was looking at individual galaxies and how they spin, and they were spinning far too fast on the outskirts, again, far too fast to be able to be held together by the gravity of the matter that we could see. So they proposed that there was this dark matter out there that was the stuff that was holding the galaxies together. And at the time, it wasn't really known whether that was just like, you know, little planets, or like maybe black holes floating around, or things, maybe our laws of gravity were wrong and we needed to fix them. But these days we think it's probably a particle, but not a particle that makes up the stuff that you and I are made of. It's not light, it's nothing in our standard model of particle physics. But it could be a particle that just is everywhere, but just doesn't like hit stuff. It doesn't bounce off stuff. So it just passes through the Earth without being touched.
So it seems unlikely that there's sort of hidden galaxies made of this stuff.
Yeah, I mean, there's potentially clumps of dark matter out there, but they would typically be dragging all of the normal matter into themselves as well, and therefore you end up with the dark matter and the normal matter being basically in the same place. But there might be some like differences out there where you get patches of one or the other. But that's only one of the dark things in the universe, because the other thing that we call dark is the dark energy, and it has like the opposite effect to dark matter. Dark matter, we think, clumps, it clusters, it holds galaxies together, and it has an attractive gravitational pull. Dark energy, we think, pushes. It accelerates the galaxies away from each other, and it means that the entire expansion of the universe is speeding up for some reason. So we don't know why that acceleration of the expansion is happening, so we give it the name dark energy. And again, it could be something weird like the energy of vacuum itself. It could be that we need to adapt our laws of physics to explain it. So we're trying to figure that out at the moment.
So you mentioned it's causing the expansion of the universe. Does that mean it sort of acts in like an anti-gravitational way? Yeah,
so we knew for ages that the universe is expanding, right? All of the galaxies are moving away from each other. Space is essentially being created in between the galaxies. But ever since that was discovered, people were wondering, is it going to expand forever, or is it going to recollapse? And that's sort of like asking, do galaxies have the escape velocity from each other? So escape velocity on Earth is how fast you would need to go to jump off Earth and propel yourself up into space and never return. And on Earth, the amount of speed that you would need to escape Earth's gravity would be 11 kilometers per second. So pretty fast, but you know, a conceivable number. And then if you jump at 11 kilometers per second, in the absence of air resistance and the absence of anything above you, you'll escape from Earth and never come back. So the question was, do galaxies have the escape velocity from each other? Because we knew that galaxies should be pulling each other together, And so if they're all moving away in the expansion of the universe, that expansion should be slowing down as it gets pulled in. But when people were finally able to measure this in the 1990s, that was when the surprise came that they're not slowing down at all. The expansion is speeding up. So something is pushing instead of pulling. So yeah, there's some sort of anti-gravity stuff out there potentially, or for some things that making gravity work in reverse when you go onto really large scales. And it's super exciting to try and figure out what that is.
Awesome. So what kind of tools do you use to investigate this? Would that be like using the Square Kilometre Array or like the Hubble telescope?
Yeah, so we use all of the telescopes we can get our hands on to try and measure these things, and we try and measure them in as many different ways as possible. So the acceleration of the expansion, for example, was discovered, the strongest discovery that we had came from supernovae, so these exploding stars. There's this particular type that always explodes to about the same brightness, and so by looking at how bright they appear, you can tell how far they are away. So that's super useful in astronomy, because often you can't tell whether this thing you're looking at in the sky is something that's bright really far away or something that's faint nearby. So if you know how bright it is intrinsically, that means you can get rid of that ambiguity because you know how bright it is, so you can tell how far it is away by looking at how bright it appears. So if you can measure the distance and the speed, you measure the speed by looking at how the light shifts into the red if it's moving away. Then those two pieces of information can tell you how fast something's moving away from you and how fast the universe is expanding. And we measure that at many different distances. And because when you're looking over many different distances in astronomy, you're looking back in time, you can tell how fast the universe was expanding in the past and compare it to how fast it's expanding now. And that's sort of how the acceleration of the universe was discovered, sort of the discovery of dark energy. There was plenty of hints before that the universe was accelerating, but it wasn't really sort of taken massively seriously until that point. But there are all sorts of other ways in which we measure it. Even the simple age of the universe is an indication that the universe is currently accelerating. Because if you look at the ages of the oldest stars are 13, 14 billion years old. And if you look at how fast the universe is expanding now, and look at if it had slowed down to reach the current speed, then the universe was only like 9.5 billion years old. And so there was all people were complaining, hey, the stars are older than the universe. Obviously that's a problem. But if the universe is currently accelerating, then the age of the universe is much longer than people had initially calculated. So we think it now slowed down initially and then started to speed up. And that makes the universe about 14 billion years old. So phew, it's older than the stars, everybody's happy. And so even simple things like that indicate that there's something going on, like there's acceleration. But we've measured it in so many other ways, measuring the distribution of galaxies in the universe. We've measured both dark matter and dark energy by measuring the bending of light as it moves around clusters of galaxies. And we've measured the cosmic microwave background, which is the leftover afterglow from the Big Bang. And these are all completely different ways to measure the existence and how much dark matter and dark energy are out there. And they all come up with the same numbers. And so it's a real great confirmation from many different sources that there is something definitely out there that we need to explain. And we know lots of the properties of dark energy and dark matter, like what the strength of gravity is, how much they cluster, and how fast they move, and that kind of thing. But we don't know what they are yet. And that's where the puzzle lies, that's where the mystery is, and that's the excitement of studying this field at the moment.
So you're here in Perth now. What caused you to visit?
So we're here in Perth right now to celebrate the 100 years since an observation that was made in Western Australia of an eclipse which confirmed Einstein's theory of relativity. So Einstein's theory predicted that light would travel a curved path as it went near a really massive object like the sun. And there was an eclipse in 1922 that occurred across Australia, but the best place to view it was up on the coast of Western Australia at this place called Wallal. And they sent an expedition there to observe it, and what they were looking for is whether the apparent positions of stars appeared to move when the sun passed in front of them. Now normally you can't see that because the sun's really bright, but during an eclipse you could measure that. So they looked at the stars like around in the background of the sun during the eclipse, and they noticed that instead of being where they thought that they should be, they were moved out further. And that's what you would get if the light was bent towards us, because the light that should have been coming from this angle was coming from a bigger angle than it otherwise would have. And that makes things look like they're further away from the sun. And so that was a really exciting moment in physics, when it really convinced the scientific community that this weird theory of general relativity, where time and space can warp and bend in response to matter and movement, that was right. And that's sort of one of the revolutions in physics, basically, in the last century. So it's a really exciting moment that occurred 100 years ago.
So the confirmation of Einstein's general relativity is what led to the discovery of gravitational waves, right? Those are now being used in a new type of astronomy. How important do you think they are in the field of astronomy now in astrophysics?
Gravitational waves are awesome. It's as though we've been able to see for our entire lives, but we were deaf. And initially we didn't know that sound even existed, and then people were like, hey, there's this thing called sound, but no one had experienced it yet. And now we've finally been able to sort of hear the universe. Everything until 2015, when the first gravitational waves were seen, pretty much everything we had seen and knew about the universe came from light. It might have been radio waves, it might have been X-rays, it might have been optical light, but it was all just light, and a few charged particles from cosmic rays. And that all changed in 2015 when we got this new way to sense the universe, and it completely opened a new window on the kinds of things that we can observe. We can't see black holes by the light they emit, but we can see them by the gravitational waves they emit. And so it opens up a whole new realm of possible discovery, which is ridiculously exciting. For me, who's been trying to understand dark energy and dark matter and understand the expansion of the universe and how that accelerates or changes with time, the gravitational wave mergers are an absolute wonderful tool, because you can use them to measure distances. And unlike supernovae, where you have to sort of calibrate how bright they are by using like parallax nearby and then Cepheid variable stars and stuff, then find supernovae in the same galaxies as these variables and measure their distances, and there's this whole sort of messy sort of distance ladder where we sort of calibrate one thing on the next to figure out how bright things are intrinsically and use those to measure distances. That's not necessary for gravitational waves, because we have a theory that predicts how bright they should be given the mass of the black holes or the neutron stars or whatever it is that's colliding. And because we know how intrinsically bright they are essentially from theory, it sweeps away that entire uncertainty about having to calibrate it with nearby things. So it's a really, really pristine tool to measure distances. Basically, as soon as you measure the changing frequency as the objects orbit each other and then get faster and collide at the end. And that changing frequency over time tells you how heavy they are, and once you know that, you can calculate how big the amplitude of the gravitational wave should be. And so you measure the amplitude here on Earth, and that tells you how far they are away. So we're really, really excited to use these to hopefully try and clear up some controversy in astronomy at the moment, where people have measured the expansion rate of the universe, not the acceleration, just the expansion rate, in different ways, and they're sort of disagreeing. It's like not terrible, but like it's getting to the point where people are like,
so this is the current expansion rate?
Yeah, so the current expansion rate is known as Hubble constant, and it's how fast the universe is expanding right now. And it's always been a controversial number because it's very difficult to measure. But people have measured it using things like the cosmic microwave background, the afterglow from the Big Bang, or measured it using supernovae, these exploding stars. And the answers just don't quite agree. They've sort of had big error bars initially, and as they've been getting more and more precise, they've been focusing in on numbers that are not quite the same. And is this a sign of some interesting new physics that we have not understood? Or is this a sign that we've stuffed up the measurements in one or the other? At the moment, we're not sure, but gravitational waves are the perfect way to confirm or refute the measurements of the supernovae, for example. So I'm really excited about the prospect of using those over the next few years to measure the expansion rate of the universe and really see whether if they end up agreeing with the supernovae, it could be that there really is a genuine problem with our theories that we need to fix. If they end up agreeing with the other measurements, then it's more likely that that there was a sort of a stuff up in some of the supernova measurements. But if they agree with the supernova measurements, it might mean that the other ones just stuffed up their measurements. It won't solve the problem completely, but it will definitely shed light on whether we need new theories or better measurements to explain this weird thing we're seeing.
Approximately 100 years ago, we used the Wall eclipse to prove Einstein's theory of general relativity. With this upcoming eclipse, are there any other key measurements that we're going to be taking this time?
I think the upcoming eclipse is going to be a really fantastic experience for the people who get to observe it, because you get to see astronomy in action. You get to see stuff passing in front of the stars. You get to understand the orbits of like how we really are orbiting the sun, and the moon's orbiting us, and all of these sort of things. And I think it's really, really cool. And I've regrettably never actually been able to see an eclipse myself, but everyone who I've heard of who has seen them say that it's absolutely amazing to go and see. So I'm hoping to be able to see this one.
What did inspire you to get into science originally?
It's hard to say. None of my family had gone to university. I didn't really know that science was a career I could do. I certainly didn't have any aspirations that I was going to be an astrophysicist when I grew up. But I do remember as a 10-year-old watching Halley's Comet and being just astounded, not by this beauty of this thing that's stretched across the sky, but by the fact that humans knew enough about it to predict that it was going to come back in 75 years or so. And just that, to a 10-year-old, 75 years seems like forever. So to think that we understood physics well enough to be able to explain those kind of things, I remember being in awe of that at the time. And that's the first thing I remember about being excited about science. I also got excited about the space program, and there was some famous space shuttle launches. I used to love watching these, and I loved science fiction stories. And when I heard about relativity and the warping and bending of space that occurs, that blew my mind. And I think I remember hearing about that in about grade 10 at school, and being inspired by that. That might have been one of the moments where I was like, yeah, this would be a really cool thing to study.
If you were to give a piece of advice to anyone sort of heading into a science career, people coming out of high school, what would your piece of advice be?
100% do the hardest maths and physics that you can at school. They're the absolute best place to learn it. Don't forget to also do coding, some sort of software. Learn to do some computer programming. That's going to be really important in any STEM career that you do as well. And when you do go to university, don't just concentrate on your studies. Make sure you do all sorts of other things as well. There's a huge amount that you can learn at university and in life in general that's outside the classroom. Go play sport, do music, join clubs, do an exchange to a different country. Get as many different experiences as you possibly can, because all of those shape what you become as a person and how well you can do in whatever career you choose. If I could answer one question, I really want to know what dark energy is, because I think the answer to that is going to give us a huge insight to how we can combine quantum physics and general relativity, our theory of particles with our theory of gravity. And that's sort of the holy grail of physics at the moment, to be able to put those two theories together. I think one way to get more people into science is just to keep the fun in it. It's not this dry subject where you sit down and do maths all the time. It's very creative, and getting people to understand how creative it is, how much you have to use your imagination and you have to figure out things that no one's ever figured out before. It's a really exciting and difficult but rewarding thing to try and do. And so if you like solving puzzles and going exploring and venturing, then doing research in STEM is a really, really great way to go. I'd also say that there's a bit of a perception out there that if you want to get a job after university, that you need to do something that has a specific title to it, like engineering or something like that, whereas physics or physicist or astrophysicist, that doesn't really have an obvious, you're going to go out of university and do some job associated with it. But there is such a diversity of opportunities that you get when you have the skills that you get as a physicist, and there is no shortage of jobs at all. There is a huge demand for graduates, and I find that people don't really get that. They think that if you study physics, there's not too many options of what you can possibly do, and that's completely wrong. So if we can get people to understand just how much exciting stuff there is to do with a science degree, that will also help people get into it.
Thank you so much for your time, and it's been a really interesting conversation.
Yeah, thank you.